All right, my friends, welcome back to your regularly scheduled notes. Haven't seen one of these in a while since we've got the Pi Day and all that other good stuff taken care of. But right before spring break, we're going to talk a little bit about introducing this concept, something I think is very important if you plan to pursue higher math. Okay, maybe not so much if you don't plan on doing it, but either way, should help you in figuring out how to form logical statements either way. So today we're talking about trig identities. Okay, identities. All right, so if you remember your geometry days, okay, we had a bunch of like sections dedicated to proofs, okay, and like properties of triangles and angles and all that other good stuff. This is pretty much a follow-up to that. Okay, we're still working with trig, of course, so we're going to be mentioning the unit circle here, but it's time to put on those thinking brains, okay, because what I'm about to say is mostly going to be kind of in that realm of logic, where I'm trying to prove that some things are equal, okay, or some things that match. So, what are identities? Okay, well, an identity, okay, is an equality. Okay, so an equation basically, okay, where any chosen value for the variables is true. You might remember from algebra, basic algebra, that the identity property, okay, is basically just saying that A equals A. Okay, very, very simple. That is an identity. If I pick any value for A, you would probably agree that A is A. If I said A is 1, well, 1 is 1. Perfect. That makes sense, hopefully, to you. But this, we're going to move on and talk about this in the context of trig. Okay, there are two identities we're going to take a look at today, and they are mostly things you should be familiar with. It's just kind of applying it on that next level. Okay. So remember your stuff from before. Okay. The first identity, I'm going to change my color here to identify that it's the first one we're talking about, is called the Pythagorean identity. Okay, so even now, when I just said the word Pythagorean, there should be some big flags heading off in your head saying, oh, wait, I know Pythagorean theorem. That's easy stuff. So, okay, this is based off of course, the Pythagorean theorem. A squared plus b squared equals c squared. Okay, hopefully you know this from your algebra days, maybe your geometry days. Okay, but it basically tells me that I add up the square of the two sides of a right triangle, and it should give me the square of the hypotenuse. Okay, so that is hopefully not news to you. You may have to dig back in your brain and figure out that again, but hopefully that is nothing new. Now, how are we going to apply it and adapt it to fit our trig functions? That would be our sine and our cosine. Well, let's consider the unit circle. Okay, so I'm going to draw a circle here. I'll do my best. Okay, so here's my unit circle, and I've got like my axes here, my x and y. Okay, call this my x and my y axis, and this is the unit circle. Remember, the unit circle has a radius of 1, okay, which if I take any old triangle in the circle, let's take this one for example, okay, that length will be 1. And then I have these two triangle sides, right here. Okay, so far so good. You're still following me? Now the unit circle is what we're going to use to kind of make this Pythagorean identity come true. Okay. So what do we know about this triangle, and what do we know about the unit circle? Well, the unit circle, well, I just said radius is 1. So if you were to write the unit circle's equation, which I think we talked about earlier, okay, the unit circle equation is this: x squared plus y squared equals 1. Well, okay, Mr. Who, you've told me that this is the equation of a circle, and yeah, I think I get that. That's pretty straightforward. What does that have to do with the Pythagorean theorem? That's talking about circles, and that's talking about triangles, right? Well, here is the triangle in the circle, right? And you can see the point that I made, the 2 points. One is at the origin, one is on the circle itself. Okay, that point on the circle allows us to form this triangle, where this side, the horizontal side, represents an x value, and the vertical side represents a y value. Do you see where I'm going with this? And of course, the radius is 1. Okay, Hopefully the gears are turning in your head. So hopefully you're looking at that triangle and say, wait a minute, this formula looks pretty similar to what we just wrote up here with the Pythagorean theorem. The triangle has sides x and y, and the hypotenuse is 1. Well, 1 squared is 1, right? So you could actually consider there's a square here. Perfectly fine there. And so hopefully you're making the connections here. This Pythagorean theorem can be applied to our unit circle, okay, to find the points, right? To find the points. And of course the triangle inside of it too. All right, now you're wondering, okay, you've done all this for me now, Mr. Who. But where's sine and cosine? You said you were going to talk about those. That's what I'm getting to. Remember, very early in the semester, we talked about how we equated sine to y and cosine to x. This is where we come and bring those ideas back together. Okay. Now that I know that x is supposed to be cosine and y is supposed to be sine, I can rewrite the equation as a final way of doing it. Cosine squared theta, because that's what we're talking about, an angle here, an angle theta, okay, plus sine squared theta equals 1. Okay, if you've been kind of tuning out, you've kind of been following along, listening to my voice, this is very important. This right here is the epitome of our Pythagorean identity. Basically, if you leave the notes with nothing else, you just need to know this guy. Okay, and how to use it, of course. Now, what's it mean? It means if you square the value of cosine theta at any angle theta, and you square the value of sine theta at any angle theta, the same angle as the first one, you add those two values together, and you should get 1. Okay, and that's the very, very basic proof of how this Pythagorean identity came into being. That is the first type of identity we're talking about today, and the second one is very, very simple. I'm going to pull up some examples on the delta math to kind of show you where exactly this is going and why we even talk about these identities in the first place, at least for the purposes of higher math. Okay, so let's hold off to that for now. Let's talk about the second type of identity. The second type of identity is something you probably have already seen in this class. They're called reciprocal identities, and that's basically just working with the reciprocal trig functions. Okay. That would be, of course, your secant, cosecant, and cotangent. Stuff we've seen before, nothing too new. And hopefully you remember from our talking about it previously that secant and cosine are reciprocals, cosecant and sine are reciprocals, and cotangent and tangent are reciprocals. Okay, so maybe nothing new there, but here's how the identities would go. You know this from the procedure we've done in the past working with these, that you basically just take cosine, and you could say that this is 1 over secant, or the other way around, right? Secant is 1 over cosine, okay, because they have that reciprocal relationship. These are also identities. So these guys right here are the identities for our reciprocal functions. And you can do the same with basically every other one, okay, right? Cosecant is 1 over sine, okay. Cotangent is 1 over tangent, and vice versa. If you wanted to put tangent over some reciprocal there, you could say tangent is 1 over cotangent, so on and so forth. Okay, that is the second major identity we're doing. Finally, there's like one last minor one. I'm going to kind of slot it in here with the green. Okay. This one kind of follows from our identities that sine and y are equal and cosine and x are equal. But here's the last little identity. It's that tangent is supposed to be sine over cosine. Okay, you may remember that from when we talked about it way far back. Okay, but now it's time to bring it back. So I'm going to star this one because I'm not going to focus on it too much. You should already know this. Okay, but these are all the basic identities you're going to need in order to complete the IP and succeed in higher level math. Okay, so let's go ahead and look at our delta math, and let's take a look at some problems. Okay, so you can try them in class as well. All right, so I'm back here with our delta math, and I'm looking at our Pythagorean trig identities module. You're going to have to do a couple of these in order to pass the IP, but basically, the reason we talk about identities now rather than later, like maybe you're waiting till calc to do it or whatever, the reason we do it is because they're very useful in helping us substitute, okay, So I'm going to write that up here really quick. Identities help us substitute, okay, which, if you remember from last time with the equation, can help us solve or simplify equation. Okay, so that's kind of the main purpose of our identities in this class. Okay, if you decide to take calculus after this, they are going to be very helpful, especially when you get to the parts where you're talking about sine and cosine and all their derivatives and all that good stuff. But of course, that's not here, so don't worry about that. Okay, but the directions here say to simplify the expression to a single trig function, no denominator. Okay, so basically they're just looking for a final answer that is one trig function and nothing else. Okay, so it's one sine, or it's one cosine, or it's one tangent. They're not being added, they're not being multiplied, nothing like that. Okay, you might have a squared in there, but that's besides the point. So let's think about this. Here's 1 minus cosine squared x. All right. If you need to have the identities out, I'm going to go ahead and write them out real quick again. We had our Pythagorean one, which is sine squared plus cosine squared equals 1. Okay. We had our reciprocal ones, which this one doesn't look like it needs it, so I'll skip it for now. And then we had the sine, cosine, tangent one, where tangent is sine over cosine. We don't need that one either. So let's think about this. We have 1 minus cosine squared x. Okay. Here's my Pythagorean identity. Okay. And here's what I have. If I want to consolidate this to one statement, I'm going to need to do some substituting with this identity in order to do that. Well, if you look at what we have right now and what we had for the identity, hopefully you can see that they share something in common. They share this 1. Okay, 1 on the right side, of course, is all alone. And here's 1 as well. So right here we can implement our substitution, okay, where this becomes sine squared x plus cosine squared x, right? Because that's what we call the identity. That's the same as 1. And we still have a minus cosine squared of x. Okay. And then we just simply combine our like terms, right? Cosine squared and cosine squared go together. It's one of those and one of these, but one of them is negative, so they should end up canceling each other out. And I'll end up with a wonderful single trig function, sine squared x. Okay, sine squared x. This is a very, very basic one, okay, but all the identities in this section are essentially based off of our Pythagorean identity. And you might have to use a couple other identities to get there and rearrange the parts, but let's go ahead and put our sine squared of x in here, and let's submit our answer, and bada bing, bada boom, okay? Now, they do it maybe a little differently with delta math, but you can do this substitution however you want, because math is beautiful like that. Right, let's see another one. All right, I'm back here with a second example. This time it's, pretty similar looking, but instead of cosine, we now have our cotangent. So, well, the Pythagorean identity doesn't have cotangent in it. So we're going to take a couple of different steps to make sure it sets up to where we want it to work. So follow along here as I work with this. This is probably about as complicated as this gets. First of all, cotangent you should understand is 1 over tangent, but we also know that tangent is sine over cosine. There's that wonderful identity I said before, right? And if cotangent is 1 over tangent, then you could also say it is cosine over sine. Okay, it's the flip of our original statement, our tangent. Okay, so I'm going to rewrite this very quickly. Okay, 1 plus cosine squared x over sine squared x. Okay, so that was useful. Now we're talking sines and cosines, which is what we need for our Pythagorean identity to work. And it might be tempting to switch out the 1 for sine squared and cosine squared like we did in the last problem, but there's also another way we can change this 1. We can change it so that it has the same numerator and denominator, okay, in order to add our terms together. Okay, so watch this. I'm going to turn my 1 into sine squared over sine squared. Now, hopefully you agree that this is the same value as 1 when you divide these out, right? But now they have the same denominator, which allows us to add these two things together. Okay, it allows us to add these two things together. So let's do it. Combine our numerators, so sine squared x plus cosine squared x all over the same denominator, sine squared x. Okay, well now, sine squared x and cosine squared x in the top, wow, that's really simple. That's just our Pythagorean identity. This is 1 over sine squared x. And lo and behold, let's think about it. We need no denominator. And I know there's a reciprocal trig function for this too. It's cosecant. So we should have cosecant squared x as the final one trig identity. You might not be able to see that because my camera's in the way, so let me move this all for you. There we go. And let me draw the arrows to actually indicate that I'm going over there. Sorry about that. Okay, so that's the hardest this gets pretty much. Okay. There are probably some other ones in there, here or there, but you can always ask about it in class when we get to it. All right, last little example here. This is in a second module called reciprocal trig identities. Okay, very similar to our first module, except you're going to be using the reciprocal trigs, which is stuff like cosecant is 1 over sine, cotangent is 1 over tangent, and secant is 1 over cosine. So you're going to be using these to help solve these ones. Again, you're still trying to find a single trig function, no denominator. So when you think about multiplying tangent and cosine, okay, what might be helpful is to just change this to sine over cosine using the same old tangent identity there. And when you multiply by cosine, stick a 1 under it. All right, well, now when you multiply these across, cosine and cosine will cancel, and you'll just get sine of theta, it looks like. So let's go ahead and put that in real quick. Sine theta. Submit, and ta-da. Okay, so when you think about these identities, really just think on a simpler scale and figure out how you need to manipulate the numbers you see and the functions you see in order to get it to become just one trig function. And that's our start with identities. All right, we're going to talk about many, many more, okay, at least between now and a little bit after spring break too. But that's our first foray into it. If you have any questions, make sure to ask in class. Maybe you rewatch a couple parts, pause and go back if you need to rewatch it. I will see you guys in class. Let's talk about it there.